Hey everyone, welcome to another video. Now we're continuing on with this idea of multiple outcomes here in this particular video. So we're talking about setting up arrays, which we'll talk about in a minute, for what we call two-step experiments. Now this experiment, you hear this word in the context of science a lot. We're gonna more be thinking about this as something like an event, or you can call it like a probability experiment, but we're more or less looking at just two events happening after one another. So examples of these two-step experiments is something like flipping two coins. Two coins. Or selecting two socks from a drawer, for example. So two socks from a drawer full of socks, and we can look at the probability of what you're going to be pulling out. But in both of these examples, we have the idea of multiple events happening. And as a result, we're looking at getting multiple outcomes happening. Now, there are two particular examples of these experiments, or two possible ways the experiments are conducted. So one is going to be with what we call with replacement. So that is hopefully something self-explanatory, but let's go into it for a second. So with replacement would be something like, I don't know, measuring the probability of one thing, say pulling a ball out of a certain color ball out of a bag of balls, and then measuring that probability, putting it back in and doing it again. So we have replaced the ball. We've taken it, but then put it back in after conducting the experiment or looking at the probability. And the other is without replacement. So, let me actually draw this in because it may help with visualizing this. So if we had, for example, a bag of balls, so I have two red colored ones and I have two purple, one green. With replacement means we take one out, we measure the probability of selecting one of these, for example, or we measure, the probability of pulling this one out, and then we replace it, we put it back in before measuring the second probability. Now, this same thing down here, to look at without replacement, what that would look like is we say take out one of these balls, let's say this one, we take it out, we measure some kind of probability, but we don't end up replacing it. So when we measure the second probability, this guy is still outside, and we are measuring something with the next ball that gets pulled out, with what's left in the bag in this particular example. So that's how we can think of with replacement and without replacement. And that will come pretty soon once we start looking at some examples. So let's jump into those now. So we're going to look at an example of an event or a sample space of probabilities for events with replacement. Okay, so here we are looking at two coin tosses. So I have my first coin here that gets tossed, and my other one gets tossed either at the same time or right after. Now, when you flip a coin, or you flip one coin, then flip it again, none of the probabilities change. There's no replacement happening. There's always going to be the same amount of outcomes. The outcomes don't change. So with replacement, our outcomes don't change. So we flip one coin, we get a head or tail. It's not like when we flip it again, we're going to get our only possibility is going to be a tail. Our outcomes are not going to change. So we're always going to get a head or a tail. Now, what we're going to do here, we want to, in part A of this question, to draw up a table to list the sample space, or list all of the different possibilities we can get. So I'm going to draw something, and for some of you who watched the previous video, you will notice it looks a lot like the two-way tables we talked about in the previous video. So my two tests here, I'm going to call this one T2 for toss 2, and this is going to be T1 for toss 1. So I have my heads, I have my tails, and in this one I have my, I'll draw it here, my heads and my tails, and this is going to be toss 1. Alright. Okay. So what are going to be my possibilities with replacement? So that means that my outcomes aren't going to change. I toss something, get heads or tails, and the second time I toss it, I have, again, my two options are only heads or tails. My outcomes don't change. So if I toss my first one, I get heads, and my second one, I get heads. I can write this on the table as, let's do a different color, HH, for a head followed by another head. If I got a tail first, then a head, I can write this as TH, tail then head. I can get a head first, then a tail next, or I can get two tails flipped. So my actual sample space, so my total amount of outcomes here, my sample space, in other words, we just mean our set of total outcomes. That's going to be head, head, tail, head, head, tail, and tail, tail. Okay. So that's part A. We've drawn this table and listed this sample space. Now for part B, I want to find the probability of obtaining a head then a tail. This is what my notation means. A head followed by a tail. So if we look at our sample space here, there is only one possible outcome happening out of all of the ones we have here, and that's going to be this one over here. Flipping a head for toss 1 and then getting a tail for toss 2. So I have my, to set this probability out, I have my favorable probability, so the one that I am looking for, getting a head tail, so that's going to be 1, over the total amount of outcomes. So I have my favorable outcome over my total outcomes. Now how many outcomes do I have in total? Well, I have 4 outcomes in total. Heads, heads, tails, heads, heads, tails, tails, tails. So that is going to be my probability. I have a 1 in 4 chance of getting a head first, followed by a tail. So the order here matters. Our question has asked for probability of getting a head followed by a tail. And only one of these is going to be present from our coin flip. Now, the second probability, the next part of this question asks for the probability of getting 1 head. Okay, so let's consider our sample space. So I have head, head, tail, head, head, tail, tail, tail. Well, it's not going to be this one because we're only asking for one head. This gives me 2. And tail, tail also doesn't contain a head in it. So I can choose from tail, head or head, tail. No matter which order we get these in, I'm going to end up with one head, which is what the question is asking of me. So my probability then is going to become my number of favorable outcomes. So that's 2, my tail, head, then head, tail, over my total amount of outcomes, which is once again going to be 4. I only have 4 possible things to choose from here. And this simplifies to 2/4 or 1/2. All right, now we've looked at with replacement. Now we are going to be looking at, in the second part of this video, at events without replacement. And we'll see what that means in a practical context. Okay. Now, this question tells us that 2 letters are chosen. So, this word 2, we're looking at a 2-step experiment. So 2 letters are chosen from the word tree. Without replacement. All right, without replacement. So, what this means is when we take out one letter, so say we take out the T, I only have these 3 remaining to choose from. Whereas with replacement would be, okay, I take this out, measure the probabilities, then put it back in. But here, once I take the letter out, I have to choose from the remaining letters. So once again, we're going to list all the outcomes from this particular 2-step experiment on a table. So I'm going to draw a nice big one here because this is quite a wordy question. So I have my first letter and I'm going to list all my letters here. T, R, E, E, and I have my other ones here. Make myself some more space. T, R, E, E. Alright. And this is going to be my second go around. So drawing this array here, now I can be in a really good position to list everything. And once again, same with the Venn diagrams and two-way tables from the previous video, the hardest part is just laying this all out. Everything else becomes a lot easier. So we'll list the outcomes here. So, well, here, if I draw a T first, is there any way I can draw another T if I'm doing this without replacement? Well, no, because we said if I take this T out, I only have R, E, and E to choose from. So my probability for getting, there's no chance I'm actually going to draw another T after I've drawn my first. So that is actually not an option for this particular two-step experiment. Because we're looking at without replacement, the T is not getting replaced. We've pulled it out, so we only have the remaining letters to choose from. This particular thing is impossible. So our next option is getting R and T. This is possible. I can get E and T, and I can get E and T. This is okay because I've pulled out a R first, an E first, and another E first. So it makes sense that for all of these, I have another t, a t to choose from, because it hasn't been taken out yet. Only here, this can't be possible. All right, the next one, we have t and r, that's possible, but r and r is not possible. I can't pull out an r after I've already taken one out. That would be the effect of, say, taking this r away. I'm left with t, e, and e. So drawing another r is impossible here. And I have this particular e and r, and a second e and r here. Okay, so moving on, I'm going to do this a little bit quicker. This one works, this one works. This one here, even though there are two e's in the word, we have pulled out, in this example, the third e. So we cannot pull out that identical e another time. I can pull out the other one, but I have taken this one away. So I can only choose from the second e, not the first. So that's not possible, but this I can do, because I'm using the other e. Alright, almost done here. T, E, R, E. This time this can work, because I've got my first e, and then my other e I can still use. E and E. And this time, for my final thing, it's not going to work. It's not going to be an option, because that's the effect of trying to get rid of this fourth letter and then trying to draw the fourth letter again. It's not going to happen. We can't draw that second e twice. Okay, so these are all of my possible outcomes, and we're going to use this to answer the following questions. So find the probability that the two letters chosen are both E. So the probability that I draw an E and then another E. So I want to locate these options on my table. So I have 1, 2. So I have two favorable outcomes. And with all probabilities, I write this as a fraction over my total number of probabilities. So if I count these, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have 2 out of a 12 chance of drawing E than E. Or I can write this as 1/6. And finally, this is where the wording is important, the probability of at least 1 E. So this means this is going to be sort of different to, because remember in the previous example we said 1 head, or if I wrote just 1 E, whoops, 1 E, I would locate the ones with just 1 E. But this at least means 1 E or more. So we have to locate any time there is 1 or more E's, or in other words, at least 1 E. So I have this here, 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 and here, here, and here. So how many of these do I have? I have 10 favorable outcomes over the total amount I have, which is 12, and this simplifies to 5/6. But this is how we can work through these types of tables and how we can distinguish between the wording of with or without replacement. But once again, the hardest part is just getting our two-way array looking really nice, so that when we get to the actual questions, it's just a matter of reading off the outcomes. But that's all for today. Thank you so much for joining me, and I will see you in the next one.